In this video, I want to talk to you about small sample tests of hypothesis for a population mean, and you're going to notice that a lot of these notes look pretty similar. There's some small changes, but pretty similar to the large sample video that I made as well. There's 4 steps in a test hypothesis, the same 4 we've been talking about for a while. The first is you need to identify or formulate the test to conduct, and that means you need to identify the null and the alternative hypothesis, and the same rules apply. The null is going to have a parameter, it's going to have a hypothesized value, and there's going to be an equal sign. So because we're working with a population mean, we're going to say the mean is equal to, mu is equal to some number, 100. The alternative is going to have 3 options for that alternative. It's going to have the not equal to, but it also has the less than and the greater than possibilities. And so that's something you're going to have to determine from the test that you're conducting. Sometimes it's really easy. Someone will say test to determine if the mean exceeds 100, in which case you'd use a greater than test. Sometimes the wording's a little tricky, and I've deliberately chosen an example that's going to make it a little bit more challenging for us to identify the alternative hypothesis. So we'll see that in a bit. But you're basically going to have your typical null and alternative. And if I write this, mu is equal to 100 versus the alternative hypothesis, mu is greater than 100, if I stop there and don't tell you any more, you can't really tell whether this is from a large sample or a small sample problem, because the null and the alternative are going to look the same regardless of the sample size. And so the sample size doesn't play a role in step 1. Where it does play a role, however, is in the test statistic. And the test statistic, as we said before, is the sample data combined in a formula. The computer's going to do this work for us to give us a number. The last time I went through these notes with you here, I used a symbol that was a Z. Now I'm going to use a T because that's the distribution that comes into play. When we're working with a small sample size, and when we're talking about means, the sample size we're working with now is n less than 30. It always makes me worry when I write this on your notes or say it out loud. This is the sample size that applies to means. The next topic I'm going to cover deals with proportions, and 30 has nothing to do with the sample size. So if you're working with means and the sample size is less than 30, that's a small sample problem. The central limit theorem's gone. It won't help us. So we can't get to the Z distribution. A guy named William Gossett, who we talked about with the confidence intervals, he said sometimes a T distribution will work, but it only works if the population of X's that we're sampling from is approximately normal. That's going to show up again as an assumption. We saw it when we worked with small sample confidence intervals for mu. We're going to see it again when we're working with small sample tests, a hypothesis for mu. So the first step is exactly the same. The second step, we're changing distributions. What we're doing is the same. We're using the sample data to try to get a feel for where our sample tells us we're at, but the distribution changes. If the null hypothesis is true, which again, we're still assuming the null is true, we expect this number to be near 0. So if this number is near 0, that's going to support the null. The further that gets from 0, the more evidence we have to suggest that maybe the alternative is correct. And if we're doing a greater than test, we're expecting a positive number. If we're doing a less than test, if the alternative is right, we're expecting a negative number. And if we're doing a not equal to, well, then who knows? All bets are off. We're expecting either. So those are the first 2 steps. The third is we need to evaluate the test statistic. Now, these notes are going to look a little different than what you saw before because we have a new technique. We have the rejection regions. We're going to state values of the test statistic that are unexpected and lead us to reject H naught. Okay, just like we talked about before, rejection regions. The rejection region work is on you. Now, with small samples, you're going to have to go into the T distribution. Oops, and I missed a T here. That should be T. And we're going to find the critical values. Now, because I have a 2-sided rejection region here, the assumption would be this would be the rejection region for a not equal to test. If I was doing a greater than test, I'd put all the alpha in the upper tail. If I was doing a less than test, I put all the alpha in the lower tail, and we'd get 1-sided rejection regions. But the point is you have some work to do. Rejection regions mean more work for you. You have to work with the table, the appropriate table, a T distribution in this case, to come up with the rejection region. Except now, I've talked about p-values. In between the first time I went through these steps with you and now, I've talked to you about p-values. And the p-values, typically we're going to find the p-values on a printout. Now, what I've told you is I'm going to make you find p-values in a table probably one time. But if I'm going to make, or when I ask you to find the p-values in the table, I'll make sure you're working with a large sample. So when I'm working with a small sample test hypothesis, which is what these notes, what this video, what this lecture is about, I'm going to be giving you a printout, or you're going to be generating your own printout to use. And so the p-value is going to be on the printout. Now, I've talked to you about the printout p-values. You have to be a little careful to make sure the printout p-values are giving you the p-value that you want for the test you're conducting. I'll mention that again in the example, but it's always a question. So the printout will give you a p-value. You need to make sure if it's the right one. And we've talked about if there's any question in your mind, go back and review the p-value information that I've talked about, and you can look at that conversation again. But you're going to find a p-value, and then we go on to the fourth step, which is our conclusion. And the conclusion depends, the way we make our conclusion at least, depends on which of these evaluation methods you're using. If you're using rejection regions, then you're going to compare your test statistic to the rejection region. Does it fall in the rejection region? In this case, is it bigger than 1.842? Is it less than negative 1.842? If you say yes, then you can reject. If you say no, it's not either of those things, then you would fail to reject. For the p-value method, you just compare alpha to the p-value. It's very simple. We talked about in the prior lecture, the p-value lecture, when p is low, you can reject the null hypothesis, and it's kind of it has a ring to it. When p is low, reject the ho. That's a really easy way of remembering how to use p-values to make conclusions. So if we're rejecting, we would say add alpha. There's always different alphas we're going to be testing. We reject, there is sufficient. If we're failing to reject, then we add the I in the end. There's insufficient evidence to indicate that HA is true. So the same four steps are in play. Okay, test, identify the test statistic, evaluate the test statistic, make your conclusion. We're using a different distribution now. We're using t-distributions, and they only work if the population of x's that we're sampling is approximately normal. So just like we saw with small sample confidence intervals, there's an extra assumption that's necessary. There's two assumptions that we've talked about this semester so far. The first is we need random samples, and that's the easiest assumption that we have. Because whenever we're doing any kind of inferential technique, confidence intervals, test hypothesis, doesn't matter, we're always going to need to assume that the population we're sampling from, we randomly sampled from that population. Let me say it that way. The second assumption, and it's only needed if we're working with small samples, is that that population is approximately normal. And it's the x's. So whatever it is you're working with, if you're working with people, people can't be normal, but the variable that you're working with, so if you're talking about ages of students, for instance, you would need to assume that the ages of all students is approximately normal. If you're talking about any quantitative value, and we'll take a look at an example. I'll go through the example in a second with you. So those are the four steps. Here's the example I want to take a look at. The skidding distances along a new road in a European forest, a very specific example, were measured at 20. Now notice that number. Let's get a red pen here. 20 randomly selected road sites. Now, before you jump on and say that's a small sample, make sure you're working with a mean. Now, think about it. Skidding distances. These are trucks. These are tractor trailers, actually. When they skid, when they hit the brakes and they start skidding, imagine, if you will, the skidding distances, or how far a truck skids. That's called a skidding distance. It's going to be a number, right? And it's measured in meters, and the data are not shown below. I did not copy the data, but I have my notes, and I'll tell you what that looked like. Let me go to the skidding distances. These numbers are kind of impressive, actually. Let's see if I can find it here. Bear with me. Here we go. The first truck skidded 488 meters. The second one, 350 meters, then 457, then 199 meters. And so you can see the quantitative data varied from one skidding distance to the next. But whenever you're working with numbers, okay, whenever you're working with numbers, someone's going to be interested in the mean. What's the average skidding distance? When I'm working with yes, no data, for instance, did the truck skid off the road, yes or no? We're not going to be interested in average. We're going to be interested in what proportion skidded off the road. So we're going to have proportions from qualitative data, which I'm going to do in the next lecture, averages or means from quantitative data. We've seen that before with confidence intervals. It's a trend. It's pretty consistent. So we're going to be testing a mean because we're working with quantitative data, and we have a small sample because n is less than 30. A logger working on the road claims that the mean skidding distance is at least 425 meters. So that's our expert in this case. We're going to go to a logger working on the road, and he or she claims that the mean skidding distance is at least 425 meters. Now, this is the part that's a little tricky. Is there sufficient evidence to refute this claim? And we're going to test it in alpha of equal 0.10. What's the null and the alternative that you wish to test? Okay, the parameter, remember the test has a null and the alternative have a parameter, they have a hypothesized value, and they have some signs, equal, not equal, greater than, less than. You've got to figure that out. The parameter is easy in this case. It's mu. It's the average of the numbers. Mu, the specific value, the hypothesized value is 425. The null is going to say the mean is equal to 425. The challenging part here is what are we trying to show? The logger claims the mean is at least. The logger claims mu is greater than or equal to, that's their claim, 425 meters. How do you refute that? Well, what does refute mean? Refute means, how do you show that that's wrong? How do you say that the logger is incorrect? Some of you guys are already thinking it, right? We're going to show that the logger's wrong. We're going to do a less than test here. We're going to test to see if the population mean is less than 425. Because if we can say mu is less than 425, we can go back to the logger and say, guess what? Logger man, you're wrong. Or logger woman. Okay. As I mentioned when I went through the 4 steps, I said sometimes it's really easy to set up the alternative hypothesis. Sometimes it takes a little thought. This one was a little bit tougher, a little bit harder to find. If I would have said test to determine if the mean skidding distance is less than 425 meters, that's really straightforward. This one's a little bit more challenging. Some are easier than others. All right, so that's the test. That's the first step. Now we need to go and create a test statistic. And in order to do a test statistic, that's where we're going to take these 20 skidding distances, which I didn't show you, right? And we're going to put them in the computer and we're going to get a printout. We're going to let the computer do the math. And notice that the null and the alternative, and a lot of times students are like, why do I need to know the null and the alternative? They show up here on the printout. Well, the reason they showed up there on the printout is because I specify. Go watch my video showing you how to generate these printouts, and you can see where I actually put those pieces in. I have to put the variable in. Distance is the variable, the mean distance, and then I had to put in the value 425. I actually had to type that in, and I had to choose the less than option. So I'm specifying the alternative. The reason they show up on the printout is because I've already identified that that's what we want to test. The test statistic is right there, negative 2.53. That's a number that you're always going to get on a printout. I want you to spend any time at all doing calculations. So our test statistic is negative 2.53, and now you need to evaluate that. And I want to do this 2 different ways. I want to do the rejection region approach, and I want to do a p-value approach. All right, rejection region approach. We have an alpha of 0.10. The rejection region says, all right, we need to figure out what's the critical value. So we're drawing a curve. And a lot of times when you see me draw this picture, I say, oh, it's a z, but in this case, it's not. It's a t-distribution with n-1 degrees of freedom. I've mentioned to you how degrees of freedom are kind of a pain in the butt. For a lot of things we do, the degrees of freedom is n-1, not everything. But for our purposes, when I ask you to use a t-distribution, you can think n-1. I want to simplify that. It's centered at 0 as well. I have a 0.10 alpha that I'm working with in this problem. I take a look at the alternative and I see, ooh, there's a less than sign. So we put all that 0.10 in the lower tail of a t-distribution that has 19 degrees of freedom. And we find this cutoff point, we call it a critical value, that has 10% below it. So I need to go and find a table. Look at that. There's my t-table flying in here. And so I'm going to go to the 0.10 column, and I hesitate to, well, I can erase them later. I'm going to go to the 0.10 column. I'm going to go down to 19 degrees of freedom, and I'm going to match them up, and I'm going to see this number here, the 1.328. That's this number, except it's a negative 1.328 because I'm on the lower side of the curve. And so I'm going to reject H0 if my test statistic falls further out here. That's called the rejection region, and this is how I'm going to write it. Now I'm going to come and clean this up a little bit. I'm going to take a couple of these marks out of here. We're going to reject H0 if our test statistic, and again, that should be a T. I don't really care, honestly, if you wrote that as a 0 T. I get the idea, but technically we should talk about our T distribution if T is less than negative 1.328. That's the rejection region. That's the tabled work, and I'll mention that phrase, and again, that's why I wanted to accentuate that. That's a tabled work. You have to, rejection regions require you to go to the correct table and find the cutoff point, find the critical value. And now the conclusion says, well, let's compare our test statistic, sorry about that, to that. Where is the negative 2.53? Well, it falls a lot further out here. The negative 2.53 falls way out in the tail. We can reject. So the rejection region, we compare the test statistic. Is the test statistic less? Yeah, it's a lot less. We can reject. There's sufficient evidence to indicate that. Remember, reject, sufficient. And then this part here, when we're rejecting H0, really what we're saying is we believe the alternative. We believe mu is less than 425. You've heard me say this before. This is kind of the copy-paste part. Take the wording of the problem and just paste it in here. Mu is less than 425 meters. And when I talk about the mean skidding distance of all skids is less than 425 meters. Can we refute the logger? Yeah, we can. The logger says it's at least 425. I'm going to go back and find that logger and say, hey, logger guy, logger woman, you're wrong. At alpha equal 0.05, with 95% confidence, I believe you're wrong. That's how we do a test of hypothesis. That's using the rejection region approach. Now, see all this work right here? That was you running to the T-table showing me you know how to go do a rejection region. Let's take a look at the same problem now, but let's take a look at it from the p-value approach. So the null and the alternative are the same. The test statistic's still a negative 0.53, but what's the p-value approach ask us to do? Well, in the p-value approach, we got to find the p-value. There it is. Now, where does this come from? Let me kind of review this with you. The p-value comes from this picture right here. There's a t-distribution with 19 degrees of freedom. Okay, it's centered at 0. So our p-value said draw the distribution, draw in the value of the test statistic. So way out here is there's a negative 2.53. And because we're doing a less than test, we're going to shade out here. That's the p-value that we're shown as 0.0103. That's what that represents. That's the p-value for our test. Now, I mentioned to you the p-values are a little tricky because you got to be careful. They're given to us on printouts, but sometimes some software only gives us not equal to tests. And so if instead of the less than test, if there was a not equal to test presented, in addition to the shaded region you see out here, it would also, if it was a not equal to test, it would shade the same region out here, and it would give you the p-value, and it would actually report the p-value. If this was a not equal to printout, it would report the p-value as 0.0206 because it would have 0.0103 in both tails. And so you have to be careful. You have to make sure when I ask you to do the test of hypothesis using the p-value in the printout, you got to make sure that the direction of the test that's being tested is the one you want. In our case, it is. That's why I could just take that number right off the printout. But sometimes the printouts are going to give you different alternatives and you have to be able to adapt. If I was given a two-tailed printout but wanted to do a one-tailed test, I got to know to take that p-value on the printout and split it in half. So if I can use the p-value on the printout as long as I adapt it, as long as I get the p-value I want. And then once I have the p-value I want, all I have to do is compare it to my alpha. Is P low? Is 0.01 less than 0.10? Well, if you're dyslexic, that's a problem. Sorry about that. And I know some students struggle with that, and that's a real thing. But 0.1 is less than 10, right? P is low, you can reject the hoe. And alpha equal 0.05, and that shouldn't say 0.05. Gosh, I did terrible with my copy and pasting. Sorry about that. At 0.10. At least I'm catching them as I go through here, right? It gives me something to talk about here. At alpha equal 0.10, we reject. What would we do if we were using alpha equal 0.05? P still low, so technically that's a correct answer, but the alpha you test at should be the alpha that's asked for in the problem. In fact, what alphas allow me to reject? Anything above the 0.0103, right? So if I was testing an alpha equal 0.1, 0.09, 0.08, 0.07, 6, 5, 4, 3, 2, 0.02, I can reject. There is sufficient, that's our reject word, evidence to indicate that. And again, I'm going to say mu is less than 425 meters. Now, you saw me write or draw this picture right here, right? The p-value picture. This problem didn't ask you to do that. This problem just says use the p-value on the printout. And so sometimes I'll get students to say things like, I like p-values better because there's no table work, and it makes me want to cringe a little bit. There is a table going on behind the scenes. There is table work. It's just if you use the p-value approach, you let the computer do the table work for you. I think it's a smarter approach. P-values and rejection regions always get you to the same answer. Doesn't matter which approach you use. It's just, do you want to do the table work with the rejection region, or do you want to let the computer do the table work for you? That's the way I'm going to choose, if I can. All right, one more piece to this. Okay, the conclusion's the same as if we use a rejection region. What's the assumption that's necessary? Okay, I could have written this in the rejection region approach because it was necessary there. What's the assumption that's necessary? Well, because we have a small sample, we need randomly, well, because we have any sample, we need randomly selected data. That doesn't have to do with large or small, but because it's a small sample, we also need the population of X's to be approximately normal. What's the X's here? Tractor trailers? No. Roads? No. What's the variable? The skidding distances. We need the population of all skidding distances to be approximately normal. If that's true, then this analysis works great. If that's not true, then this printout, this analysis, there's a technical term for it. Ready? It's crap. It's garbage. The assumptions need to be true. I'm a stickler for assumptions. You're not going to like that about me when it comes to test time, but I'm a stickler for assumptions because here's what I know. It's really easy to generate these printouts. We can get them. It's really easy to take, oh, look at that p-value. P's low, reject the hoe. It's really difficult to stop and think and say, hey, should I look at that p-value? Are all the assumptions that are needed, are they all true? Are they all met? If they are, I can interpret that p-value. But if those assumptions aren't met, then this p-value here would be just garbage. So I'm going to ask you a lot of assumption questions, more assumption questions than you want. So just something to be thinking of, and I'll help you work with that as we go through the rest of the semester. Right now, there's only 2 assumptions. There's 2 more that are on their way. So that's a small sample. Not a lot changes. Really, we're doing exactly the same steps. The big thing that changes is we need that extra assumption. The assumption is the distribution of all X's in the population, skidding distances in this case, is approximately normal. So that's our small sample test hypothesis. Take a look at some homework problems and get your questions answered, and good luck.